In this video, we're going to be talking about quantitative energy problems. So how can you quantitatively, how can you get a number? How can you calculate the actual energy or temperature during a energy scenario? So our first question is a cup of coffee at 140 grams. A cup of coffee that is 140 grams cools from 75 degrees Celsius down to comfortable room temperature, 20 degrees Celsius. How much energy does it release to the surroundings? So the first thing you need to do is draw a cooling curve because the coffee is cooling. So here I have a cooling curve, and now we need to identify which part of the cooling curve is actually occurring. Well, let's first label our cooling curve just so we can identify this. So the hottest thing, again, this is temperature, this is time. So our hottest state of matter is a gas. It cools down by condensing. Into a liquid, and then the liquid could freeze into a solid. So we have a solid, liquid, gas. But in this scenario, we're only dealing with a liquid. The coffee is a liquid the whole time. So we're at this part of the curve, which means that temperature is changing. Since temperature is changing, think about what kind of energy is being released. When temperature changes, we have a release of E therm. Whenever we have a release of E therm, we need to use this equation in order to calculate our energy. So Q is energy, M is mass, C is heat capacity, and delta T is change in temperature. Okay, so in this case, let's label what numbers we actually have. So we're given 140 grams. Well, grams is mass. So 140 grams is our mass. And it cools down from 75 degrees Celsius to 20 degrees Celsius. So our change in temperature, we need to figure out the change. So we'll have 75 degrees Celsius minus 20 degrees Celsius. So we'll have 55 degrees Celsius. That is our change in temperature. That's our delta T. If you look at the top of this worksheet, it gives you a few constants: heat of fusion, heat of vaporization, heat capacity of a solid, and heat capacity of a liquid. Well, we need the heat capacity, but since we're at the liquid, we're going to use the heat capacity of the liquid. So that's 4.18 joules per gram degrees Celsius. Okay, we want to figure out how much energy, and that's our Q. So our Q is our question mark. How much energy does it release? So we just need to really plug in these numbers. So Q, that's what we're trying to find, equals 140 grams times our heat capacity, which is 4.18 joules. And this slash means per gram degree Celsius. So it's like per 1 gram and 1 degree Celsius. And then we have our delta T, which is 55 degrees Celsius. So I want you to notice that degrees Celsius cancels out and grams cancel out. So our unit for energy is going to be joules. So go ahead and multiply that out, and you should get 32,186 joules. Well, since we have two significant figures here, two significant figures here, we have three significant figures here. Our lowest number of significant figures is 2, so we're going to round to 2 significant figures, so we get 32,000 joules. And there is 1 kilojoule for every 1,000 joules. So you could also write this as 32 kilojoules. Either answer is fine. Problem number 2 says, suppose during volleyball practice you lost 2 pounds of water due to sweating. If all of this water evaporated, how much energy did the water absorb from your body? Since we're talking about evaporation, are we talking about a heating curve or a cooling curve? We would have to be talking about a heating curve because evaporation is the change from a liquid to a gas. So here is our evaporation. So we're talking about this part right here. okay? So I want you to notice this is flat. Evaporation is a phase change, so this is phase energy, and temperature is not changing. So we need to use our other equation, Q equals mass times either heat of vaporization or heat of fusion. So you use heat of fusion when there's melting or freezing, when you're here. And when we're up here, when we're at vaporization or condensing, we use heat of vaporization. So we're going to call that HVAP. Okay? So in this question, we are trying to figure out how much energy did your body, did the water absorb from your body? So our question is energy. So Q is our question. We are told that you lost 2 pounds of water, and our heat of vaporization is 2,260, and this is at the top of your page where it says heat of fusion, heat of vaporization, heat capacity, and so on. So it's 2,260 joules per gram. So we need our mass to be in grams. It must be in units of grams, but we're given a mass of 2.0 pounds. So we need to convert it into grams. Well, we're told, or kilograms at least, we're told that 2.2 pounds equals 1 kilogram. So we'll have 1 kilogram and 2.2 pounds, and our pounds cancel out and we'll be left with kilograms. So we have 9.1 kilograms. So 2,260 joules per gram is the same thing as 2,260 kilojoules per kilogram. Okay, that's exactly the same thing because kilojoules is 1,000 times bigger than joules, and kilogram is 1,000 times bigger than grams. So we're really doing like 1,000 divided by 1,000, which gives us 1. So our number doesn't actually change. So we can write it like this. And since in this question we want our answer in kilojoules and we have kilograms, we're going to use this. So we have Q equals our mass, which is 9.1 kilograms, times 2,260 kilojoules per kilogram. So our kilograms cancel out, we'll be left with kilojoules. We get 20,566, and we need 2 significant figures, 3 significant figures. So our lowest number of significant figures is 2, so we'll round to 2 significant figures. So we get 21,000 kilojoules. Okay, number 3 says, suppose that during the icy hot lab, 65 kilojoules of energy were transferred to 450 grams of water at 20 degrees Celsius. What would the final temperature have been of the water? So all it's talking about is that heating curve lab. So it tells us that we have water. Okay, so water is a liquid, so we're somewhere in here. And we are giving it energy. Energy is transferred to it, so I know it's a heating curve. Okay, and we're dealing with this section. So this is thermal energy. Okay, so I'm going to use the Q equals MC delta T. Okay, so in this case, it tells me that I have 65 kilojoules. Well, kilojoules is a unit of energy, and it says 65 kilojoules of energy, so I know that that's my Q. That's going to be 65 kilojoules. And I'm told 450 grams, so that's the M. And our C is a constant, so that's at the top of the page. So since we're dealing with liquid water, our C, our heat capacity, would be the 4.18 joules per gram degrees Celsius. And it asks for us to figure out the final temperature. Well, we have the change in temperature. Change in temperature is equal to the final temperature minus the initial temperature. It doesn't tell me the change in temperature. It tells me the initial temperature, which is 20 degrees Celsius. But in order to find the final temperature, I'm going to need to know the change in temperature. So this is my first question mark. What is the change in temperature? So I have my Q, I have my M, I have my C, but I want you to notice this is kilojoules and this is joules. So again, 1 kilojoule is equal to 1,000 joules. So this would become 65,000 joules. Okay, and I want you to try and solve for the change in temperature first. Okay, so that's algebra. And then solve for the final temperature. So for number 4, you're doing the same thing, but now we have iron. So instead of water, we have iron. But we have the same mass of iron. We are given the same amount of energy and the same final temperature. But since we have iron, our specific heat changes. So we're told that our specific heat, or our heat capacity, is 0.447 joules per gram degree Celsius. So we're not going to use that anymore. We will use our heat capacity of iron. Okay, do your best on the rest. Please just attempt them. Show me some work. Show me at least your curve. Is it heating or cooling? What section are we dealing with? Figure out, is it thermal energy? Do we use this equation, or is it phase energy? Will we use the other equation? So just show me thinking. I know you can do it. Thank you all for being wonderful students.